In Chapter 6, we revisit trigonometry, and we're going to learn a completely different way of thinking about the trig ratios, especially sine and cosine, that doesn't seem to really have anything to do with right triangles. And you will understand how to interpret the sine and cosine of angles that are bigger than 90 degrees, even bigger than 180, or even bigger than 360. So these are obviously not angles you can encounter in a triangle, let alone a right triangle. Toward the end of the chapter, we're going to learn a couple of laws that will allow us to apply trigonometry to triangles of any shape, not just right triangles. But at first, we're going to look at sine and cosine in a sort of very special way, and we have to start with some terminology. So if you imagine an xy axis, xy coordinate plane with an x-axis and a y-axis. When we talk about an angle being measured in standard position, or an angle in standard position, what we really mean is an angle, and in the diagram I've got the angle labeled theta, measured between the positive arm of the x-axis and another line segment connecting the origin to a point. That point is called the terminal point, and the line segment connecting them is called the terminal arm. The angle is measured in a counterclockwise direction, meaning that if the terminal point were all the way down on the x-axis, that would be an angle of 0 degrees. And as you move that terminal point or that terminal arm in a counterclockwise direction, you're going in a positive direction. The angle will get bigger. Which right away, a little preview of what's to come, gives you a way to interpret a negative angle. A negative angle really just means you're starting at the positive arm of the x-axis and you're going in a clockwise direction, but we'll see that later. So let's take a look at a straightforward problem with this new terminology. If you're given a terminal point, point P, which has an x-coordinate of 3 and a y-coordinate of 4, can we determine the trig ratios of theta and determine theta itself? Well, this is actually a pretty straightforward question and doesn't really require much more than any of the trig you had from last year. So let's draw the diagram first. And we'll draw in the terminal arm. There's your point P, 3, 4. And to help you do this, the easiest thing to do is to create a right triangle. And the right triangle you want to create is one where you add a vertical. You could create a right triangle by adding a horizontal leg, but that will get a little bit confusing. It's much easier to add a vertical line to create a right triangle, and then we can refer to this angle in the right triangle as theta. So that's theta as measured in standard position. Now, the point has an x-coordinate and a y-coordinate. The x-coordinate is 3, which means that the horizontal leg of this right triangle is 3 units, and the vertical leg is the same as the y-coordinate, 4 units. So we can now find the 3 trig ratios: sine of theta, cosine of theta, and tan of theta. Now, if you remember your acronym, SOHCAHTOA, sine is the opposite over the hypotenuse. So we don't have the hypotenuse. That should be the next thing we need to do. And you can use Pythagoras to find the hypotenuse. In this case, it's a little easier because I've chosen legs of 3 and 4. And hopefully you remember a few special triangles. This one has a hypotenuse of 5, but you could figure that out using Pythagoras if need be. So now we've got everything to find all 3 trig ratios. The hypotenuse, or rather the sine, is opposite over hypotenuse, which is, in this case, 4 over 5. The cosine is the adjacent leg over the hypotenuse, which is 3 over 5. And the tangent is opposite over the adjacent, 4 over 3. Now, just a quick aside, a bit of a review here. Since the sine and the cosine are always one of the legs divided by the hypotenuse, and the hypotenuse has to be the biggest side in the triangle, sine and cosine always have to be less than 1. At least in a right triangle, they will always be less than 1. Whereas the tangent, because it's the ratio of 2 legs, can be bigger than 1. All right, now we're going to need to keep that information in mind a little bit later. Now, what about the angle itself? Can we figure out a an approximation in degrees for the angle? Well, yes, we just have to use the inverse functions, which are arcsine, arccosine, or arctan. And since we know all three ratios, we can use any of them. But if you're actually doing this in a problem, I would suggest using the arctan, because we are given the two coordinates, which means we're given the opposite leg and the adjacent leg. We didn't have to do any extra work to find those numbers, whereas we did do a little more work to find the hypotenuse. And if I made a mistake there, then I'm just going to be compounding my mistake by using arcsine or arccosine. But of course, we're pretty confident 5 is the right answer here, so you could actually verify that the arcsine of 4/5 is going to be the same as the arccosine of 3/5 is going to be the same as the arctan of 4/3. But as I said, let's just use tan. So theta is equal to arctan of 4/3, and when you punch that into a calculator, you get 53.1 degrees. If I don't specify, just round things to the nearest tenth of a degree. Now, if you get a funny result like 0.92, that means you're in radian mode. So make sure you know how to change your calculator from degree mode to radian, or rather from radian mode to degree mode. And anytime you get some kind of weird looking answer like that, just make sure you're in degree mode. Now, let's do this, or at least look at this sort of diagram a bit more generally. The length of the terminal arm is often symbolized with an r, and why we use r will become evident fairly quickly. So there's our right triangle, and if we have a point with x and y coordinates, again, the vertical leg of the triangle here is just simply the y coordinate. I mean, that's what the y coordinate tells you, how many units you are above the x-axis. And the x coordinate is the horizontal leg, because that's what the x coordinate tells you, how many units you are to the right of the y-axis. Now, let's just think about our ratios sine and cosine. The angle measured in standard position is this angle right here. So the sine of theta is equal to the opposite over the hypotenuse, which is y over r. If I multiply both sides of that equation by r, I get an expression for y. Y is just r sine theta. And if I do the same with cosine, I have cosine theta equals x over r. Then I get x is equal to r cos theta. So I actually have expressions now for x and y, and I can say that the point P here is, instead of x and y, it's actually r cos theta and r sine theta. Now, this in itself is incredibly useful because it allows you to take a length, r, a particular angle from the horizontal, and break it out into its horizontal and vertical components. And you'll do this a lot in physics class. You'll have r will be called a vector, and it has a particular direction and a particular length, and you'll be able to break it out as to the horizontal length and the vertical length. Or it might represent a speed, in which case you have a horizontal speed and a vertical speed. Very, very useful. But I want to go one step further. What if we let r equal 1? And you'll, in the next diagram, see why we use r. If we let r equal 1, what do we get? Well, if you look at the expressions for x and y above, when you let r equal 1, essentially it disappears, and you get x equal to cos theta and y equal to sine theta. And so this point up here has coordinates of simply cos theta sine theta. Now, I've got this circle ready to go on the right. If I bring this circle over so that it just fits on top, you can now see why we chose r to represent the terminal arm, because you can think of it as a radius of a circle. Now, when you have a circle radius 1, we call this a unit circle. It's centered at the origin with radius 1. And any point on the circle, you can determine the x and the y coordinate by just simply taking the cosine of theta measured in standard position and the sine of theta measured in standard position. Now, this is actually a complete breakthrough because it gives you an entirely different way of thinking of these two functions, cosine and sine. And in fact, if you've ever heard them referred to in another way, it was probably as circular functions. And the way we first learned about them had to do with right triangles. It didn't seem to have anything whatsoever to do with a circle. But now you can think of cosine as simply the x-coordinate as you move around a circle. And the sine is simply the y-coordinate as you move around a circle. It also allows you to understand the results you get when you look at a table or you punch into a calculator the cosine and the sine of 0. Obviously, we've never seen a right triangle with an angle of 0. There's not really much of a triangle left if you have an angle of 0. But since this point on the unit circle is the point 1, 0, it now makes sense that the x-coordinate 1 corresponds with the cosine of 0. And the y-coordinate 0 corresponds with the sine of 0. We can also make sense of 90 degrees. If you go to the top of the circle, you can see that that has a coordinate of 0, 1. And so the cosine of 90 degrees is 0, the x-coordinate. And the sine of 90 degrees is 1. That's the y-coordinate. We can now also understand, well, what happens when you get bigger than 90 degrees. If you're bigger than 90 degrees, it just means you're over here in quadrant 2, or perhaps further in quadrant 3 and 4. And you can see that as soon as you move over into quadrant 2, the x-coordinate goes negative, which means that the cosine is negative, but the sine is still positive. So you can experiment with this by taking sine and cosine of some angles bigger than 90. And by the time you get over here to 180, you're at negative 1, 0. So the cosine of 180 is negative 1. The sine of 180 is 0. And at the bottom of the circle here, we are at 0, negative 1. And sure enough, the cosine of 270 degrees, that's 3/4 of the way around the circle, is 0. And the sine of 270 degrees is negative 1. 360 degrees takes you all the way back to the start. And so the sine and cosine of 360 is really just the sine and cosine of 0. And so we've got this totally different way of thinking about sine and cosine, and also a different way to refer to points on the circle. You can refer to points on the circle simply by the number of degrees. So 100 degrees means you're starting at the point 1, 0 and moving along the edge of the circle 100 degrees, which takes you over into quadrant 2. We'll look at this in much more detail in the next section.